Today we will begin looking at Unit 2, and to begin the whole unit we're going to talk about the derivative function. The derivative of f at x at a number a is given by f prime of x, which is equal to the limit as h approaches 0 of your f at x plus h minus f at x over h. Recall that this is very familiar to you, as this is the same as when you're finding what your slope is. So this f prime is just read as f prime. And just to discuss a couple different notations. So there's two notations that we will be looking at very rarely. And we have the Lagrange, which is just our f at prime of x. And we have our Leibniz, which is dy over dx. Now these are both taking the derivative of a function. So in example 1, we want to determine the derivative of f at x equals x squared at an arbitrary value of x. We are going to use this derivative function here when we're finding our limit. So our f prime of x is just going to be equal to the limit of f at x plus h minus f at x all over h. So this will look like f prime at x is equal to our limit as h approaches 0 of x plus h squared minus h squared. There is no value of x given here, so we just add our h to our x value all over h. So this will be equal to the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. Now what you can see here is that our x squared, are going to cancel out, and what we will be left with is the limit as h approaches 0. Now you'll see here with our 2x plus h plus our h squared, we can factor out an h. And when we factor out that h, we're left with 2x plus h all over h. And now those h's will cancel one another out, leaving us with 2x. So our f prime at x is equal to 2x. Note that this is also our slope of our tangent. Now, why is it useful to have the general derivative of a function? Well, it is useful because we can determine the slope of the tangent at any point on the curve. So for example 2, we want to determine the derivative f prime at t of the function f at t equals the square root of t, where t is greater than or equal to 0. So once again, we're going to use our limit as h approaches 0 of f at x plus h minus our f at x all over h. So our f prime at t, however in this case we'll be using t's instead of our x's. So our f prime of t of the limit as h approaches 0 of t plus h minus the square root of t all over h. Now in this question here, what we're going to need to do is we're going to need to rationalize our numerator. Recall this from our previous unit, because if we were to just sub in 0 for our h value, we're going to have our denominator equal to 0. And when that happens, we know the whole function won't exist. So we're going to rationalize the numerator. So we're going to multiply both our numerator and our denominator by the square root of t plus h plus the square root of t. Okay, and so now what we're going to do, we're just going to evaluate. So the limit of h approaches 0, and we have t plus h minus t all over h times the root of t plus h plus the root of t. Now what you'll notice here is that our t's cancel out, and we're just left with h in our numerator position, and therefore those h's will cancel out in our numerator and our denominator, leaving us with the limit of h approaches 0 of 1 over the square root of t plus h plus the square root of t. Now when we sub in 0 for that h value, we're going to be left with 1 over 2 root t. And that is our derivative of f prime of t. Now in example 3, we're going to still determine the equation of our tangent. So again, we're looking at our derivative. However, we're now going to look at when we have an x value, and our x value here is 2. So what we need to do first is we need to find what f at 2 is equal to, which is going to be a half. Remember, that's just found by subbing in 2 for our x value. And therefore f at 2 plus h will just be equal to 1 over 2 plus h. So what we need to do first, our first step is to find our slope. And to find our slope, we're going to do the limit. Okay? However, we just learned that this can be done by finding our derivative. So what we're going to do first is we're going to find our derivative, then we're going to sub in our x value. So what you could do, you could first find these values and then you could find the slope as we did in our last unit. So why don't we do that first, and I'll show you how it's very similar to one another. So we could find our slope, so our m is equal to the limit as h approaches 0 of 1 over 2 plus h minus our half all over h. Now remember, you need to find a common denominator here, which our common denominator would just be 2 times 2 plus h. So we'll have 2 minus 2 plus h all over 2 times 2 plus h. And we're going to multiply that by 1 over h. Remember, that is just about when we're dividing fractions, we flip our second function there. And therefore that will then be equal to, we're actually just going to have 1 because these 2's are going to cancel out. We'll be left with negative h in our numerator position. However, this h will cancel out with the h in our denominator. So that will leave us with the limit as h approaches 0 of negative 1 over 2 times 2 plus h. We can now sub in for our h value. So therefore we'll get this equal to -1/4, and that's what our slope would be. So then we would use our slope to sub it into our y equals mx plus b form to find what our equation of the tangent was. Now, a little bit different what we're going to do when we're doing derivatives. We're going to find f prime of x. So we're not going to actually sub in our x value here. So f prime of x is going to be equal to the limit as h approaches 0 of 1 over x plus h minus 1 over x all over h, which is equal to the limit as h approaches 0 of x minus x plus h. Remember, this is just us finding a common denominator, which in this case is x times x plus h, times our half. Sorry, our 1 over h, not half. Which is equal to the limit as h approaches 0. Again, it's very similar to finding our slope previously. Our x's are going to cancel out. We're going to have negative h, and that h is going to cancel out with the h in our denominator, which will leave us with negative 1 over x squared plus xh. Now if I sub in 0 for my h value, I'm just going to get my f prime of x, so my derivative, is equal to 1 over x squared. So since I know this, now I can say, therefore, at x equals 2, my whole function here, so my slope, is going to be equal to negative 1 over 2 squared, which will be equal to -1/4. Note that these are the same. So now you can see the continuation from Unit 1 to Unit 2. So now I'm going to take my slope value and I'm going to sub it into my y equals mx plus b form. So I will have y equals -1/4 x plus b. Now I'm going to sub in my point here. So I'm going to take the point 2.5, and I'm going to sub that in for my x and y. So I have 1/2 equals -1/4 times 2 plus b. And when I evaluate here, I'm going to get that my b is equal to 1. And therefore, our y is equal to -1/4 x plus 1. Now in example 4, we want to determine an equation of the line that is perpendicular to the tangent to the graph of f at x equals 1 over x at x equals 2, and that intersects it at the point of tangency. So remember that if we're talking about a perpendicular line and we're talking about our f at x equals 1 over x. So from example 3, so our previous example, we found that our slope was equal to -1 over x squared. And at x equals 2, we knew that our slope was equal to 1/4. So if we're talking about perpendicular, recall that perpendicular is the negative reciprocal. So if we're talking about the negative reciprocal, so of our perpendicular slope, we know it would be equal to x squared. So therefore, at x equals 2, our slope would be equal to 4. So we can do that by just subbing in 2 into our x squared, or just by doing the negative reciprocal of negative a quarter. So since we know that information, we can use that to find what our equation would be, which is y equals mx plus b. So what we're going to do is we're going to use that point that we found in our previous example, so that point 2.5, because that is going to share that same point. Both our first line and our perpendicular line are both going to share that point, so that will be their point of intersection. So at that point, we know that our y value is 1/2. We know that our slope in this case is 4, and we know that our x value is 2. So we're going to actually go ahead and solve this. So it would be 1/2 minus 8, which is equal to b, which we would get negative 15/2. So therefore our y is equal to 4x minus 15/2. Now I know a bunch of you probably are asking, do I need to keep this in a fraction? And the answer is yes. Please keep that in a fraction. Fractions are very important. You need to make sure that you are very familiar with fractions and not always using decimals. Now to begin looking at the existence of derivatives. So a function f is said to be differentiable at a if f prime at a exists. At points where f is not differentiable, we say that the derivatives does not exist. 3 common ways for derivatives to fail to exist are: our first way is our cusp point. So this is where our tangent line is vertical and the function is increasing on one side and decreasing on the other. So you notice it comes to this point and then it starts to increase. So it's decreasing and then increasing. Another common way where the derivative will fail is our vertical tangent, or our infinite slope point. So again, our tangent line is vertical and the function is increasing or decreasing in the neighborhood at the point P. And our last one is our discontinuity, which we did look at in Unit 1. And for our last example, we want to show that the absolute value function f at x, which is equal to the absolute value of x, is not differentiable at x equals 0. Now, just to graph this, what we can do, we know that the graph of this is going to look like this. However, that should be right at 0. Okay? So all of our y values are going to be positive. Okay? Our x values can be negative, but when they come out of our absolute value brackets, that means that they are now positive. That is just what an absolute value does. So just looking at that, we can note that f at x would be equal to x, where x is greater than 0, negative x, when x is less than 0, and 0 when x is equal to 0. So this, remember, is called our piecewise function. So what we can do is we can look at the limit on either side of 0. And this way we can show you that this limit itself does not exist. So if the limit doesn't exist, it's not going to be differentiable at 0. So let's look at the limit as x approaches 0 from our negative side. So we are going to have the absolute value of x plus h minus the absolute value of x all over h. So as it's approaching from our left side, note that this is going to be when it's negative, where our x values are negative, right? So this will be equal to the negative of x plus h minus negative x all over h. So when we go ahead and look a little bit further in this, our x's, because these two here make a positive, and we have a negative x, those are going to cancel out with one another. And what we'll be left with is negative h over h. So therefore the limit as x is approaching 0 from our negative side is actually just going to be negative 1. Now let's look at the limit as h, sorry, before that should have been h, not x, pardon me. So as h approaches 0 from our positive side, we look at the absolute value of x plus h minus the absolute value of x all over h. Now when we're looking at it from the positive side, so when x is greater than 0, we are going to be dealing with positives. So we just have x plus h minus x all over h. And now you can see our x's here are going to cancel out, and what we're left with is h over h. And when we evaluate that, that is actually just going to be equal to 1. So therefore, since we have one side approaching negative 1 and one approaching 1, the limit of f at x as h approaches 0 does not exist, and therefore it is not differentiable. At x equals 0. And you can also see that because this is what we would refer to as a cusp point.